Thank you very much for clicking our video. Here we are going to explain the introduction of what are polymers. You can go directly to the content that you want in the link description, or you can follow the entire video. It will be my pleasure to give you an overall view of what are polymers. Well, polymers are macromolecules that exist in nature already. We have latex, leather, proteins, cellulose, and others, natural chemicals that are considered polymers. However, since 1948, humans have learned to synthesize them. As with other materials, a different type of polymer can be created every day for each demand. Literally, every day new materials are created. And this happens also with the polymers themselves. The synthesis of a polymer requires the use of monomers. Poly means many. Mono means single or single one. Mer means part or piece. Therefore, polymers means many parts. For a material to be considered a polymer, it must have repeating units. So we mentioned that to produce the polymers, we need the monomers. To make them turn into a polymer, we need a reactor and some specific properties like temperature, pressure, and a catalyst to make the reaction happen. Then, after all those industrial processing, complex equipments, then we can have the polymer. Polymer types. Thermoplastics. They can be molded using heat process. Those can be melted with the temperature, and you can mold it in the shape that you want. A toy, a packaging, an automotive part, a bottle. Thermosets. They cannot be molded by heat. Cross-linked bonds avoids the softness of the molecules by heat. You cannot melt it without degrading the polymer itself. Elastomers. Those are mainly represented by rubbers. Those have double bonds like butadienes and isoprenes. Those double bonds create the characteristic that elastomers have. Polymers can also be divided in homopolymers or copolymers. A homopolymer is formed by a single type of monomer. For example, we have the polyethylene. We have the monomer of ethylene repeating itself in the entire molecule, only the ethylene. Meanwhile, a copolymer is formed by two different monomers. Let's see the example of ethylene vinyl acetate, EVA. You have the ethylene and you have the vinyl acetate. So in this case, we have two different monomers. There is also the possibility to have a terpolymer. These are formed by three different monomers. One example here is the thermoplastic elastomer, TPEE, isoprene, butadiene, and styrene. So we have three different types of monomers forming the polymer. No need to get afraid of this molecule if you are not a chemist. Stereoisomerism, or just tacticity, is a phenomenon that refers to the arrangement of common monomers in a molecule. They can be arranged in blocks, alternating, or random. So what does that mean? Let's take the example of a block copolymer. Let's suppose the letters A, B, C represents three different types of common monomers. In the case of a block copolymer, the common monomers are divided literally in blocks. You have a block of a common monomer A, another block of the common monomer B, and another block of common monomer C. The alternating copolymer means that the common monomers are divided in an alternated arrangement, like in the example ABC and ABC. The case of a random copolymer, the common numbers are divided in a totally random way. It's just random. There is no logical arrangement of the molecules in this case here. Why is that important to understanding the tacticity or stereoisomerism? Let's suppose that we have a same molecule, like a polypropylene, for example. If a polypropylene is a block copolymer or a random copolymer, even if it's the same type of polymer, it will show totally different properties for different applications and markets. Molecular distribution. Understanding not only the type of molecule, but also how they are distributed and their size in a polymer is essential for a better understanding of a polymeric material. The way the chains are distributed, including how they are entangled, significantly alters several mechanical, optical, barrier, and electrical characteristics. For example, a same molecule can have totally different properties. Let's see the case of high density polyethylene and low density polyethylene. They are all polyethylene, right? But due different molecular weight distribution and entanglement of the molecules, they behave totally different. It is possible to calculate the average molecular weight or the weighted molecular weight, which is more practical and realistic. There is an important concept here called polydispersity. It's an index that indicates the difference between the size of molecules. Polydispersity closer to 1 means that the molecules of the polymer have similar sizes. Meanwhile, if the polydispersity is much different from 1, it means that the molecules of a polymer they have various sizes and weights and different weights. Let's see the next slide with those graphics, broadband and narrowband. Broadband means the polydispersion is farther from 1, so the molecules of the polymer have different size and shapes. Uh, this implies that this polymer might have a lower crystallinity, lower rigidity, but also stretch more because you have uh, larger molecules and smaller molecules. So it's easier to stretch this material a little bit more. The density also have a trend to be lower. So in the case of a narrow band type of polymer, the polydispersion is closest to 1, which means that the molecules of the polymer are more or less of the same size and weight. It also implies that this polymer have a trend to have a higher crystallinity, higher rigidity, which means also a higher modulus. So it's also expected to have lower stretchability. A polymer with narrow band type, you also have a trend to have a higher density in comparison to a broad band type. Crystallinity. In general, it refers to how the molecules are organized. The more crystalline, the more ordered the molecules are. The term amorphous means no arrangement or order of the molecules. It's the opposite of crystallinity. The term degree of crystallinity can only be applied to polymers because they are macromolecules, and thus they can exhibit more and less crystalline zones. Let's see the example of the image below. Let's suppose that it represents a polymer, a macromolecule of a polymer. In the same molecule, we can have a crystalline phase or amorphous phase. The same material can have parts that the molecules are more organized, or parts that the molecules are not so organized. It's important to take in mind the crystalline properties of a material because it can change its properties significantly. Let's take, for example, the polyethylene. Polyethylene, it's possible to have the high density polyethylene, which is a more crystalline type of polyethylene. And it's possible to have a low density polyethylene, which is not so crystalline like the high density. It has more amorphous phase. The properties are totally different, and also the end use application. For example, if you need an application that requires a higher modulus resistance, then a high density polyethylene, higher crystallinity, might be a better option. Meanwhile, If we need to produce, for example, thermoformed flexible packaging where we need more stretchability, maybe a low density or even a linear low might be more interesting because you have more amorphous phase. And if you have a more amorphous phase, it means that you can stretch more the material. Important temperature properties. Melt temperature. It's when the polymer melts. It shifts from the solid state to liquid state. It is also known as fusion temperature. This is the temperature that you can start molding the material the shape that you want. Glass transition temperature. Below this temperature, the polymer becomes brittle like glass. The mechanical properties are reduced. Softening point. The polymer is not melted yet, but is about to. This temperature is also known as fusion crystalline temperature. The material can become, you can pierce it, or maybe you can even bend the material. Besides, it's not melted yet, but it's soft enough to deform the material. Degradation temperature. The polymer deteriorates. Depending of the material, the subproducts can be harmful. There is a scale below here that you can see which temperature tends to be higher or lower. But the main point here is to consider those temperature when selecting a material, since the first processing point of view to end use application. Types of reaction. Basically, there are four main types of polymerization reactions. Addition polymerization. In this case, the monomers are added one to each other until they create the macromolecule. For a good example of those polymers by addition are the polyolefins. This type of polymerization is also called gas phase polymerization. Polycondensation. In this case, moisture or water are produced by the end of the polymerization reaction. And a good example here are the polyamides. They are they are produced by polycondensation reaction. Suspension polymerization. In this case, the polymer is produced within a solvent base. For example, PVC. It's a liquid phase polymerization. And it's also possible to produce polymers by emulsion polymerization. In this case, the polymer is produced in, within an emulsion. For example, water-based acrylic resin, very common resin to use for paintings and adhesives. So before we finish, we have prepared a quiz that you can try to answer the questions. I will stop the video so you can try to answer them, and we will see if we can match our answers. Okay, 3, 2, 1. Okay, there you go. Hope you had time to answer the questions. Let's see if we can match the questions 1 to 5. Please confirm if you have answered the same questions. If not, or you have any question, please contact us. Thank you very much for watching our video. I hope I could give you some introductory information about what are polymers. And if you have any question and any additional inquiry, please contact us or leave a comment below. Thank you.